What is the biggest thing in our universe? Is it a star? A black hole? What about a galaxy? In fact, how big is the universe anyway? And what is it all made of? What is the smallest thing in the universe? Depending on the way you view our cosmos, it is either
really small
or really big. I'm Damon Scotting, and this is Astronomical, Season 2. For many of us, we are taught in school that the atom is the smallest thing in our universe. But where did the idea for an atom come from? Now, 2,600 years ago, there was a Greek philosopher named Democritus who had a very profound thought. Whilst cutting things up, he thought to himself that there must be a point where whatever it is that you're cutting can no longer get any smaller. You must eventually reach what is the building block of our universe. And he described this as atoms, which comes from the Greek words for not cuttable. Now, it wasn't until the 19th century that we realized the atom wasn't the smallest thing in our universe. In fact, it gets a lot smaller. This is an atomic model. Now, you've probably seen this before. At the core, you have the nucleus made up of protons and neutrons, and on the outer edges, you have the electrons. Now, this is a very loose idea of what an atom will look like. The reality is far different. Now, at the start of the 1800s, a man named John Dalton discovered different chemical compounds have different sizes. So in this analogy, we're going to say that this chemical compound is carbon. And when you look a little bit deeper into this chemical compound, you find individual carbon atoms, which at their core are protons and neutrons. Now, you might think that this is the smallest thing in the universe, but it actually gets a lot smaller. Protons and neutrons are made up of things known as quarks, which are very quirky. Quarks come in 6 different variations. You have up quarks, down quarks, top quarks, bottom quarks, charm quarks, and strange quarks. And depending on the way these are arranged or grouped together determines the particle it makes. 2 up and 1 down quark makes a proton. 2 down and 1 up quark makes a neutron. But you can also make antiprotons and antineutrons and a whole variety of different particles. And for many people, the quark is the smallest thing in the universe. But for some, there is something even smaller. And this is string. The idea is known as string theory, and it's based on the thought that everything is made up of small, vibrating strings. They can come in 2 different types. They can come in closed loops or they can come in open-ended loops. And depending on their vibration and frequency determines the particle in which they produce. Everything around you is made up of these vibrating strings. Now, this is the size of a proton, not the size of a quark or even the Planck length. No, they are far smaller than this, which is already an incredibly small number. The size of a proton or neutron is 0.87 femtometers. Look how many zeros there are. There's 15 zeros before you reach a number down here. It is incredibly small. That is the Planck length, the smallest possible distance or measurement in our universe. Sure, you can think of a number smaller than this, but as far as we are aware, judging by the fabric of space and time, this is as small as you can possibly get. 1.6 times 10 to the minus 35. That's 35 zeros. Think how small the proton was. Think how many zeros that is, and then compare it to the size of the Planck length. Incredible, absolutely ridiculous. And although the universe itself is very large, and we are going to explore that momentarily, the difference between the small scale of the universe to the vastness of the universe is far greater. The universe is much smaller than it is bigger. Now, as a kid, I thought that the smallest thing in the universe were cells. I was aware what molecules were, but being told that there's trillions of these everywhere you look just didn't add up. But what I could see were cells. I could see thousands of them. They were interacting with one another independently. I could see it with my own two eyes. And that's because molecules and atoms are very small. They're too small for you to resolve with visible light. They are smaller than the wavelength of visible light. So in order to see them, you have to use specialized equipment. You'd have to use an electron microscope. But if you go down to the lakes and bring back a sample of water and place it under your microscope, then you will resolve a mini cosmos. There are thousands of lives all moving about underneath this microscope, all moving around under such a small surface area. It really is incredible. Wrong glass of water. They are about a micrometer in size, which means compared to us, we are 1,000,000 times larger than they are. So as far as they're aware, we must appear as giants. We must seem incredibly big. So we're now going to move on from looking at small sizes such as bacteria, molecules and atoms to some of the biggest objects in our universe. The reason the scale of the universe is so hard for us to understand is because there's rarely any context. When we look up at the night and see the stars, we can't just pull out a tape measure and determine their size. In fact, the way we do so is by measuring their luminosity and their parallax. So we're going to look at 3 different scales: everyday objects, dwarfs, moons and planets, and stars, including the largest known star in our universe. A bit like stars, it's very hard to judge the size of space probes, telescopes and rockets without any other context that you're familiar with. Hopefully this helps you to understand their true size. So in order to make things easier to understand, I'm going to talk about the scale of the universe in 3 different stages. The first of which will involve everyday sizes. So our unit of measurement will be me. Everything you see before you is going to be to scale. And if that's too confusing, then here's a velociraptor. So, firstly, a Martian rover, or to be more specific, the Curiosity rover. I personally imagined all of the Mars rovers on Mars to be no bigger than a shopping cart. Its height is 2.2 meters, which means it's somewhere between my height and that of an elephant. Then we have the Hubble Space Telescope, our largest space telescope at the moment. Its primary mirror is 2.4 meters in diameter, whereas lengthwise it is 13.3 meters, which is very large. But this is nothing compared to its successor, the James Webb Telescope. Its mirror is 6.5 meters in diameter and will dwarf Hubble. Then we have the most powerful rocket ever launched by man. This is the Saturn V rocket. It's almost 111 meters high, which means it's almost 3 times higher than the rocket tower behind me. We're now going to move on from everyday objects to moons, dwarf planets and planets. And our unit measurement for this is going to be a bouncy ball. And the first moon we're going to start off with is one of my favorites. This is Mimas, otherwise referred to as a Death Star moon. Now this is 390 kilometers in diameter, and it's going to be our unit of measurement. So for every 130 kilometers you see, that will be 1 centimeter. Also, if the planets seem a bit smaller than usual, it's because it's cold. So the first object we're going to start with is the dwarf planet Pluto. And I want to emphasize that point. Pluto is a dwarf planet. There are a number of criteria that you need to meet in order to be a planet, and Pluto doesn't do so. Some of which include orbiting in the same plane as the Sun, which Pluto does not do, does at a 23-degree tilt. You also need to have cleared the path in which you orbit, hasn't done so. It's very small, and its largest moon, Charon, is very similar in size, meaning this could be considered to be a binary planetary system. Then we have Triton, Neptune's largest moon. So hopefully this sets the tone. There are plenty of moons larger than Pluto. Then we have Europa, which is the first of the Galilean moons. Europa is also considered to be one of our best chances of finding life elsewhere in the solar system. Beneath its frozen surface is more liquid water than there is on the whole of planet Earth. This is a world that is alive. Then, just a bit larger than Europa, is our moon, which we are all too familiar with. Then we have the next Galilean moon, Io. This is the most volcanic world in our entire solar system. It's soon followed by Callisto, and then Mercury, the closest planet to the Sun. But then, perhaps surprisingly, just a bit larger than Mercury is Saturn's largest moon, Titan. Now, Titan is the only moon to have a thick atmosphere, much like we do here on Earth. But this isn't the biggest moon in our solar system. That title belongs to Ganymede, the last Galilean moon, which is the largest in our solar system. These two moons, Titan and Ganymede, are each bigger than Mercury. Moons bigger than a planet. Who would have thought? But like I said, you need to meet certain criteria to be classed as a planet. Mercury is all alone with no moons, very close to the Sun, whereas these guys orbit around gas giants, which compared to them are enormous. Then, much larger than Ganymede, we have the red planet Mars. Next is Earth's sister, Venus. I have to say Earth's sister this time because in the first episode of the first season, I said Earth's hot sister, and I got a few comments about that. What I mean when I say that is Venus is over 400 degrees Celsius, whereas our planet Earth, is on average about 12. These are the inner rocky planets and some of the largest moons, but their size is almost nothing compared to the gas giants, the smallest of which is our most distant planet, Neptune. But it isn't too different in size to that of Uranus. These two are dwarfed compared to the other gas giants. The first is the gem of our solar system, Saturn. Now Saturn now has the most moons in our solar system with 82. It also has this extensive ring system that extends for twice as far as the diameter of the planet. And lastly, we have the god of all planets, Jupiter. It is so large that it could fit our planet, planet Earth, inside it 1,321 times, which is a ridiculous number. There is a storm on the surface of this planet, referred to as the Great Red Spot, that could swallow our planet 3 times whole. Now that is one of the most ridiculous and perhaps terrifying things that you can imagine. A storm that can consume our planet multiple times over. So that's it. These are the dwarfs, the moons, and the planets in our solar system. Which means we now need to move on to our next scale, the stars. Our closest stellar neighbour is Proxima Centauri, 4.26 light years away. And it might seem smaller than you may have imagined. Proxima Centauri is about twice the size of Jupiter. It is a red dwarf, but don't let this mislead you. The rest of the stars are far bigger, including our Sun. So now we're on the scale of stars, and stars are really big. So for this scale, we're going to say that our Sun is this size. That right there is our star. So firstly, we have Polaris, the North Star. Now Polaris, bag, son of a bitch. Oh no. Oh, I should have done that. I should not have done that. So Polaris is about 37.5 times bigger than our Sun. When the Sun reaches the end of its lifetime, it's going to swell into what is known as a red giant, 256 times its size today. Which again is nothing compared to the size of other stars, such as the Pistol Star. Then we have the super red giant that occupies the shoulder of the Great Orion constellation. This is Betelgeuse, a super red giant. But now we're going to move on to the giants of our universe. Stars so big it seems impossible to imagine. This is UY Scuti. Now you won't find a name in astronomy that sounds more space and physics than UY Scuti. It's about 1,708 times the size of our Sun. But again, even that is small compared to what was, up until last year, the largest star in our universe. This is VY Canis Majoris, over 2,000 times the size of our Sun. But as of right now, in the year 2020, there is a bigger star. As we know of right now, the largest star in our universe is Stephenson 2-18, which is 2,150 times the size of our star. So, just to put that into context, in case you don't already understand, if our star is this big, that is its size compared to Stephenson 2-18. Our Sun is nothing but a speck of dust compared to this monster. In fact, if you replaced our star in the center of our solar system with Stephenson 2-18, then the star itself would stretch out far enough to reach Saturn. It is enormous. So I suppose the question still remains, are we big or are we small? It is a common belief that the human race is special. And in many ways, we are. As far as we are aware, we are the only intelligent life forms around, but perhaps we are not appreciating the true immense scale of our universe. It's easy to take 2 steps into the woods and declare that there are no bears around, but it's also very ignorant. Moving out past our solar system, you can see the hundreds of billions, maybe even trillions of stars that make up our Milky Way. An ocean of stars, the vast majority of which make up their own solar systems. And that ludicrous thought that there might be millions of different worlds out there, each with their own forms of life, is only made all the more ridiculous as we see the billions of other galaxies out there in the universe. On this scale, every point of light, every dot, is an entire galaxy. Some smaller than our own, some a lot bigger. But when viewed on a large enough scale, our universe displays order. The galaxies are grouped together. This is what is known as the cosmic web. As tremendously vast as our entire universe is, it is only the observable universe. This is all we can possibly see. 100 years ago, we were yet to discover the first galaxy outside of our own. Our universe was relatively small, but it may in fact be just one universe of many, maybe even an infinite number of multiverses, a scale beyond comprehension. Now I think I know how you're feeling right now. You're feeling small. And if that's the case, good, because you now understand the true scale of our universe. It is enormous. It is 93 billion light years in diameter. That's 88 billion trillion kilometers, which means it's 8.8 with 23 zeros after it. It's huge. So yeah, it's easy to feel insignificant or like you have no purpose on the grand scale of things. But it's also important to have context. If you were to make a scale of our universe and had the smallest thing in our universe, the Planck length, on one side, and had the size of the universe itself on the other, then we humans would pop up around about here, which means we're a lot bigger than the average size in the universe. It's easy to feel small on our planet. Our planet is huge. It's very unlikely that you'll ever go on to explore every single country or continent on our planet. But when viewed from Saturn, it appears nothing more than a pale blue dot. And if you go further out towards the edge of our galaxy, then our star becomes indistinguishable. You cannot make it out amongst the other trillion stars. And yet, if you go all the way out to the edge of the universe and look in towards the cosmic web, then we are nothing more than an insignificant speck of dust on the grand scale of the universe. When you think about the first forms of life that appeared on Earth, they were single-celled organisms that were no bigger than a micron. Which means we now, after evolving from them, are a million times larger than they were. Now, I'm not saying we're going to grow a million times in size over the next couple of years, but the point I'm trying to make is size is relative. And compared to the small atomic scale of the universe, we are enormous. The fact that the universe is so large shouldn't scare you or terrify you. It should make you excited, because there is so much of it yet to explore. Perhaps we never will, perhaps there is really too much of it. But either way, it's an exciting life to live. I'll let you answer the question yourself. Do you feel big or do you feel small? I'm Damon Scotting, and this was Astronomical. How would you like to have your name spaghettified by a black hole in front of thousands of people at the end of every single episode? Well, now's your chance. Astronomical is produced just by me, which means the scripts, recording, editing, social media and costume design are all done by myself. And after the first 2 seasons, the budget is basically empty, which is why I'm now looking for donations towards the future of this science documentary. And they start at as little as £1. If you want to watch your name be annihilated by a star as it swells into a giant before going supernova, then you can do so for as little as £1. Or, if you'd like to watch your name be ripped apart into its individual atoms by a black hole in a process known as spaghettification, then you can do that for just £5. And then finally, for just £10, you can take your place amongst the stars where you belong, because anyone that donates to science is a superstar. There we are, and if you can't donate at all, that's completely fine. Just make sure you like and subscribe, because that also goes a very long way. Cheers.